So thank you very much for the introduction and for the invitation. So today I'm going to talk about two different applications that I've developed in the last decade concerning two different, let's say, aspects of common sense reasoning. One is the aspects of dealing with the typicality in conceptual inferences, and the other one concerns the aspect concerning the compositionality of common sense representation. And then I will try to show which are the connection with the entire cognitive architectures enterprise. So before going into the, let's say, details, I want to do a very short preamble by saying that common sense reasoning is not really a new task or a new problem in AI. So since the early days of AI, there were attempts to, let's say, model in a machine this kind of cognitive capability. And the main issue that emerged is that there were at least two different types of perspective that were taken into account. There were, let's say, cognitively inspired perspectives and machine-oriented perspectives. Now, it is important to make this distinction because if we look at the, let's say, epistemological loop that we can have in the context of cognitive AI or computational cognitive science, well, we can see that if we use the cognitively inspired approaches in order to model certain classes of problems, we also expect to a certain extent then to have the possibility of providing a sort of reverse inference with respect to the natural system that has been taken as a source of inspiration. While, of course, this cannot be really the case of let's say, machine-oriented approaches. And in order to, let's say, stress a little bit this distinction, it is important to, let's say, remember the dichotomy between functionalist and structuralist models, where functionalist models, in a nutshell, can be, let's say, considered as artificial models that share with the natural system only the same input-output specification and only a very weak resemblance in terms of how the components of the system are assembled and what are the algorithms that are implemented with respect to the mechanisms that are known to hold in the natural system. On the other hand, in the structuralist perspective, there is not only the sharing of the same input-output specification between natural and artificial system, but there is a much more constrained resemblance between how a complex system is composed, so which are the internal components, and how the mechanism or the interaction between these components is implemented by using, let's say, a cognitive simulation. These two types of models of paradigms can be seen as, let's say, extremes of a continuum. Because between purely functionalist models and purely structuralist models, you can have in the middle a plethora of different types of proposal, approaches, and applications that have, to some degree, some sort of explanatory capabilities with respect to, let's say, the natural cognitive faculty that we want to model within a machine. And the interesting thing is that it is possible to attach different types of explanation to, let's say, the different, let's say, levels of functionalist or structuralist models that we can have. The details, I will go back to this point in the last part of the talk, but let's say the details of these aspects are addressed in this book, which has been published in April. And at the end, I will try to show you which are the connection with what I'm going to talk about. So let's go now to the meat, let's say, of the presentation, which is the task of common sense reasoning. So what is common sense reasoning? We could say that this type of reasoning concerns all the type of non-deductive or non-monotonic inferences, like induction, abduction, default reasoning, and so on and so forth. But this kind of logic-based characterization is not enough, because in order to really have common sense reasoning, we have to add the ingredient of typicality. And when I talk about typicality, and this will be more clear in a second, I'm referring to the notion, let's say, introduced by the work by Eleanor Roche. And I will go in a minute to this point. Another important requirement. So this is an important requirement that should be modeled in artificial system that try to address this issue. Another important requirement is the notion concerns the notion of compositionality. So compositionality is a very irrevocable trait of human cognition, and it represents one of the, let's say, main requirements that we have about our generative capability. But when applied to the problem of common sense representation, common sense knowledge, and common sense reasoning, there is this very well-known problem, which is called the pet fish problem. Okay, it is also called the gap effect. So, in a nutshell, this problem shows how prototypes are not really compositional. So, if we want to build the prototype of a pet fish by composing the two common sense, the two typical representation of what is a pet and of what is a fish, well, we see that, let's say, the generated concept does not really, let's say, does not really inherit all the typical features of the two composing concepts, but it makes some kind of, there are some elements that allows to, let's say, to inherit some features and not others, and there is also the possibility of adding new additional features, like the fact of being red, that was neither, let's say, available in the first two composing concepts. So this is another important issue to address if we want to talk about compositionality. And I will try to show you here how I dealt with these two issues, typicality and common sense compositionality, by using two different kinds of applications that, let's say, take as a source of inspiration this tripartite knowledge representation framework that tries to connect, let's say, sub-symbolic representation, vector-based representation with also a geometrical interpretation, and the symbolic layers. So in particular, I will try to show you how the dual PEC system, which is the system that has been developed for conceptual inferences and categorization, is able to, let's say, integrate these two components of the architectures in order to, let's say, to model these typicality effects I was talking about. And on the other hand, the other framework that I'm going to show you, which is TCL, which stands for Typicality-Based Compositional Logic, is a framework that tries to integrate, let's say, the numerical component, which is, let's say, crucial also in physical system, into let's say, the symbolic, into a standard symbolic machinery. So let's start with the first problem, the problem of typicality. So typicality is a very, let's say, complicated issue in the context of quantitative science. There are different theories of typicality. One of the most famous one is the theory done by Eleanor Roche, according to which prototype, concept in our structure, in our mind, are organized as around to the notion of prototypes. So there are central elements within the structure of a category that are the ones which are more cognitively peculiar in order to make decision, inferences, categorization, and so on and so forth. And the interesting thing here is that if we take this kind of configurational representation, we also have some implication from a reasoning perspective, because by assuming the prototype theory, we also make the assumption that when we have a new item to categorize, we have to compare this new item with the prototype, so with the central element of a category. Prototype theory is only one of the theories that try to explain the typicality effect in categorical judgments. Another very well-known theory in the context of quantitative science and quantitative psychology is the exemplar theory, according to which categories in our, let's say, mental structure are organized and are represented as a selected list of exemplars, of data points that we have actually, let's say, perceived, for example, during our lifetime. Also, in this case, this kind of representational configuration makes some assumption about the inferential part, because if we take this kind of exemplar-based stance, this means that when we have a new item to categorize, we compare the new item with every and each exemplar. The exemplar usually are assumed to be in a limited number, but we have to compare the new item with every and each exemplar of a category. Now, these two theories have been seen as conflicting theories in the context of cognitive science, because they explain, and they are able to actually explain different kinds of effects, different kinds of typicality effects in categorization. However, starting from the work by Barbara Malt in the late 80s, it was much more evident that humans, for example, may have both prototypical representation of a given concept or exemplar-based representation of a given concept, and most probably also other kind of representation that they attach, let's say, to a given conceptual entity. Now, this point is really crucial because this was taken as a starting point in the design of our dual-PEX system, which is a system that tries to integrate rule-based, let's say, categorization with prototypes and exemplar-based categorization. And the, let's say, overall categorization strategies is orchestrated by using the dual process theory of Kahneman. So the system 1, system 2 theory that allows us to, let's say, provide a sort of meta heuristics in order to guide all these two different categorization strategies. So the main assumption of the dual-PEX system are these two. The idea is that we should have also in an artificial system multiple representation for the same concept. And from a practical perspective, this means that we may have different kind of, let's say, computational structure that we can use for representing different pieces of knowledge pointing to a certain conceptual entity. This will be a little bit more clear later. The other assumption is that on such different kind of computational frameworks that we can use in order to, let's say, represent different components, different knowledge components of a concept, we can, to this knowledge infrastructure, we can demand different type of reasoning. Like, for example, system 1 reasoning, so fast automatic reasoning, and system 2 reasoning, which is more controllable, sequential, deliberative, and so on and so forth. So the kind of representational structures that we used was actually this one. The idea was to have different pointers, okay, to the same conceptual entity, and to these different pointers, it was possible to, let's say, attach different kind of representational structure, like symbolic models or vector space model or connectionist models. The interesting thing here is that it concerns the assumption that it makes about the retrieval of a concept. So the idea is that when we have a new stimulus to categorize, the element that goes proxy in working memory, that's why they are called proxy types, concerns the particular type of representation, which is somehow, let's say, more similar to the stimulus that needs to be categorized. So from a practical perspective, what we did was to endow our system with a hybrid representational structure, when on one end we used let's say, we modeled the classical component with the symbolic models. And in particular, we took the OpenSci ontology in order to model this part. And on the other hand, we used a particular type of vector space model, which are the conceptual space representation by Peter Yardenforth, which are actually vector space model where concepts have a geometrical interpretation. They are considered as let's say convex regions, and in this convex region, it is possible to, let's say, calculate the centroid in these regions, which corresponds to the prototype of a concept. And it is also possible, of course, to model different kind of data points. And there are a variety of similarity metrics that can be used to measure the similarity between single data points or between regions in these spaces. Now, the new thing, because it is plenty of, let's say, hybrid system, but the new thing here is that the connection between the symbolic component and, let's say, in this case, the vector space component was not done ad hoc. So we have modeled this kind of integration between two different types of co-referring representational structure by using WordNet. So in particular, this kind of integration came, let's say, for free from the symbolic component, because OpenSci was already, the OpenSci ontology is already equipped with, let's say, WordNet Synset ID. And on the other hand, we were able to model also the vectorial counterpart with the WordNet Synset ID by integrating two different kinds of linguistic resources which are available. The first one is BabelNet, or better, its vectorial counterpart, which is called Nasari. So this is a huge, let's say, distributional resource where every and each vector is already equipped with the WordNet identifiers. And this kind of, let's say, huge distributional resource was somehow reduced in terms of dimensionality by filtering its dimensions with ConceptNet, which is the result of more than 10 years of crowdsourcing activity done at MIT. ConceptNet is a resource that allows to represent, let's say, the typical, so the common sense representation of a concept by using something like 35 to 40 features for every and each concept. So it is a very, let's say, powerful resource. So this kind of integration allowed us to, let's say, have a new resource, a new vectorial resource, where every and each vector and every and each value of this vector, every and each feature was mapped with the ConceptNet. So this allowed us to pass from, let's say, one kind of representation to another one completely, let's say, in a non-ad hoc way. And the interesting thing here is that we decided to, let's say, demand the, let's say, fast kind of reasoning component to the conceptual space representation, and the deliberative component to the, let's say, symbolic representation. And the way in which we integrated these two different types of representation is by using the dual process theory. So the idea is that there is first, let's say, fast categorization where prototypes or exemplar representations compete in order to, let's say, be retrieved. And then there is a check, a deliberative check that is done by using the symbolic component. This is a very, let's say, brief example of what I'm talking about. If we consider to have a query like, which is the big fish that eats plankton, after a standard information extraction step, where basically we build a vector query, we check the similarity between this vector and the vectorial knowledge base that returns either exemplars or prototypes belonging to a particular concept. Now, in this case, it returns, for example, the concept of whale, or better, the prototypical representation of whale. Why? Because whale share with the query all the typical features. So whale eats plankton, and they looks like they are big and they looks like fishes, so they share a lot of features with this kind of concept. However, this first result is then checked with the ontology, with psych, that tell us, well, whales are not really fishes, they are mammals. So you have to revise this kind of fast inference that you have provided. So this is a very short demo in which we show how this kind of query were integrated into the ACTAR cognitive architecture. So after doing a very simple information extraction step that translated, let's say, the linguistic input into a chunk request of ACTAR, as you can see here, what we did was to, yeah, this is the chunk request. What we did was just to query this kind of external knowledge component that was added to ACTAR by checking the results to our question. So the first result retrieved by the S1 system is shark, and then there is the check with the ontological component. And in this case, I would say that differently from the previous example of the whale, the retrieval of shark is considered as consistent. And so this close, let's say, the loop of this system. Now the system is available online, and we have evaluated the system with the results provided by both a psychological and an fMRI study involving the linguistic categorization of people for this kind of sentences. So these are common sense sentences because they just have from 1 to 3 cues. So you have just a few, let's say, cues to use in order to infer the right concept and also the right representation for a given concept. And we had, let's say, pretty interesting results in terms of both the concept categorization accuracy and also the proxification accuracy. So we also measured, let's say, how much time, how often it was not only retrieved the correct concept, but also the correct representation that was also retrieved by the humans. So this is the what we did with the dual pegs. The other, let's say, system I'm going to talk about try to address, let's say, the pet fish problem that I've briefly showed you before, which is the problem of common sense compositionality. So we developed this kind of logic that integrates 3 different kinds of ingredients. The first one is a description logic with the typicality, when we try to model also in a symbolic perspective the typical features that in dual pegs we modeled by using the conceptual space framework. This framework was extended with the possibility of adding, let's say, probabilistic axioms to typical inclusions. And also, it was necessary to include an heuristic coming from cognitive semantics in order to obtain this, to model this pet fish problem in a non-ad hoc way. So very briefly, by integrating the description logic of typicality with the distributed semantics, we were able to assert in our knowledge base inclusions of the type there is a probability P that a typical C is also a D. Okay, so this is the kind of integration that we were able to make, and of course, this kind of logic was also able to deal with some exceptions to inheritance. I don't have time to go into the details, but you find everything in the paper that I was mentioning before. Then, in order to, let's say, model the common sense compositionality of the pet fish problem, we also use the heuristic of the head modifier coming from quantity semantics, according to which when we have 2 or more concepts to combine in order to generate a new concept or a new chunk, okay, there is always one head which is the element from which we want to inherit more features, and then there are it is possible to have 1 or more modifiers. Now, this kind of framework of common sense reasoning framework allowed us to put in place a pipeline where, starting from a knowledge base equipped with real data, because the probabilities can be learned from the environment, allowed us to generate, for the problem of common sense concept combination, all the 2 to the power of n scenarios, and allowed us to select, by using the cognitive, the head modified heuristics, plus more, let's say, elements that I have no time here to detail, allowed us to model the problem of the pet fish. Now, this is important because the capability of modeling in a human-like fashion, this, let's say, common sense concept combination, was explored in a number of areas, not only in cognitive modeling, but also in computational creativity and in the context of, let's say, serendipity-based recommendation. But I want to show you here just one application that we did concerning the problem of goal-oriented knowledge generation. So in this case, the idea is that if we have an agent that has to solve a goal and that has not the possibility of retrieving the knowledge from its knowledge base in order to resolve this goal, what it can do, it can try to combine, to dynamically generate within its knowledge base new knowledge that can, on the other hand, satisfy the original goal that was not satisfiable by the previous knowledge base. And we have tested this, let's say, approach in the problem of the concept composition of objects, where the idea was that given certain goals and given a knowledge base, the agent had to try to combine one or more, let's say, concepts within its knowledge base in order to satisfy that goal. I also have here a very short demo. This is, for example, the goal here was that one of finding an object that is also graspable and that is also able to launch other objects at distance. This is the way in which the TCL reasoning framework allows you to, let's say, encode the typical features. So you have the probabilities here, and you have the symbolic label. And in this case, the system tells us that it is able to form a new concept that is able to satisfy the goal by combining the concept of rubber band with the concept of a branch in order to form a sort of slingshot. Okay. And another thing here is that we also equipped this symbolic knowledge base with the coordinate scene set ID, as we did in the previous as I showed you before in the dual packs.
Antonio, if you could finish up in 1 minute, that would be great.
Yeah. I'm going to finish. And also we had some kind of evaluation that was done on this kind of common sense, on this kind of problem of common sense concept combination and concerning the problem solving capability of humans. And we also had also here measured a quite interesting overlap between the results of our system and ones provided by the humans. Another thing, final one, is that we also explored the possibility of, let's say, using this kind of strategy, because this is actually a problem-solving strategy, as a way to, for example, extend the sub-goaling procedure of a system like SOAR, and you have the details in this paper. Last thing, if we go back to the functional versus structural distinction, it is possible by considering this tool that I have, let's say, introduced in the book that I showed you before. It is possible to map the two systems that I showed you within this kind of continuum by considering the functional structural ratio, the generality of the system, and the performance match of the output of the system with respect to the humans. And this also includes errors and psychometric measures. So to wrap up, I've shown you two different types of system addressing at different levels of representation some crucial requirements of common sense reasoning. Such systems rely on the assumption that the cognitive artificial agents should address different problems at the most convenient level, but let's say addressing this, the integration between this level should not be ad hoc, and a possible way to integrate this level could be done by using, for example, resource like WordNet. And finally, I want to stress that functional and structural models of cognition have a different explanatory power. So we should really take into account this aspect when we attribute cognitive faculties to any kind of simulation, both using, let's say, embodied agents or not. Thank you for your attention.
Okay, thank you very much for that interesting talk. I think we have time for one really quick question, kind of a comment from Pat Langley. He kind of wants, he says that there are theories like Cobweb, which combine prototypes and exemplars. And I think the embedded question there is, how is your system different than things like Cobweb?
The main difference relies on the fact, because there are also other systems that try to, let's say, address exemplars and prototypes. So the main difference is on the fact that the way in which these two kind of representations are retrieved is different. So now I don't remember exactly on CogWeb this has been done, but by following let's say the results of cognitive psychology, we implemented an heuristic according to which the first, let's say, element that is inspected is the exemplar type of representation, because this answer to this respect, let's say, a well-known cognitive heuristic and a well-known cognitive phenomenon, according to which if we have an exemplar in our memory which is similar enough to the similar to categorize, this element is always, let's say, preferred with respect to the prototype. So this is the old item effect that is usually let's say well equipped. And so this is one aspect, and the other aspect is that in our system we don't just have prototype and exemplar, but we also have standard rule-based let's say checking that is done by integrating the symbolic component. And the use of the dual process theory was important for us because it allowed us to let's say provide the sort of meta heuristics to tell, okay, we can use this first type of categorization and the competition between exemplar and prototype as system one kind of perspective, and then we can check this result that takes time, because I don't know if you remember in the demo, but the ontology takes time to provide the answer within the symbolic model. But in the meantime, you have, let's say, already that kind of first answer, which is already available in the, let's say, working memory of cognitive architectures or in the action system of an agent. So you can react in a more, let's say, sort of real time.